Up until now, we've been talking about an intellectual exercise and an engineering exercise and a construction exercise carried out by a lot of people, 600,000 in total, 99% of whom didn't know what they were building. But one day in July of 1945, the people who did know what they were building saw how it worked. And it was a tremendous shock to all of them. There had been a betting pool before the test of the gadget, so-called. That was its code name, the gadget. And Robert Oppenheimer, the director of the lab, had bet that the yield would be 0.7 kilotons, less than 1,000 tons of TNT. Edward Teller, who was always an optimist, bet that it would be 45 kilotons. And Isidore Robbie bet that it would be 20 kilotons. He won the pool. The first thing that anyone saw when the bomb was detonated was an incredible flash. It wasn't just a flash of light. It was a flash of electromagnetic energy across the spectrum, from radio waves to heat to visible light to X-rays to gamma rays. With the help of this diagram of the energies of different photons at various points in the electromagnetic spectrum, we can see the source of the damage that the bomb caused. At the low frequencies, the radio frequencies, a phenomenon called electromagnetic pulse, or EMP, was induced in instruments. So basically, if we were watching this test and we had our cell phones with us, we'd find after the test that the cell phones were all useless, because of this electromagnetic pulse of relatively low frequency radiation would destroy our semiconductor-based electronics. The electronics of the time were not as severely affected because they were based on vacuum tubes which operated at a much higher voltage, hundreds of volts. The next region of the spectrum up, the infrared spectrum, would cause the wooden and plastic parts of structures to burst into fire. Unfortunately, people also burst into fire if they're too close to the explosion. The visible part of the electromagnetic pulse could cause blindness in people who were looking in the wrong direction at the wrong time. The X-ray and gamma ray part of the spectrum could cause cancer in the long term, as the electromagnetic photons pass through our tissue. They can do a lot of ionization. They'll ionize chemicals, which will cause them to undergo chemical reactions having undesirable effects like breaking strands of DNA and so on. Between the visible evidences of destruction coming from the gadget was an invisible one, a flood of neutrons, not as fast as the speed of light, but not as slow as the shock wave. It would induce radioactivity in whatever it hit. The really serious consequence of this is if it hits a human body, because it will induce radioactivity within the body. So there is no protection from this radioactivity. Even if it's relatively low energy, it has nothing to go through before it actually deposits inside your tissues. No skin, nothing to protect you. The second observable effect was a shock wave traveling outward at about 600 miles per hour. And the last thing they saw was a fireball rising from the ground and creating a large mushroom cloud as it did so. Eventually the mushroom cloud was swept away toward the northeast by the winds. Efforts to measure the effects of the bomb were somewhat frustrated by the fact that it was bigger than anyone really thought it was going to be. So many of the instruments set up to measure the radiation were fried by the explosion. Most of the photography was overexposed because of the strength of the explosion. And there weren't really that many efforts to measure the fallout and the spread of the fallout from the site. In fact, there is evidence that some of it spread as far as Indiana. The men who saw the explosion were shocked by it. They had never seen anything so bright, nor had anyone else. The light of the explosion was visible from hundreds of miles away, even from a ridge near Los Alamos where some people were watching. It was awesome at 20 miles away, and it was overwhelming at 10,000 yards where the official observers were located. But the Trinity site was not the end of bomb testing. The first two bombing missions to Hiroshima and Nagasaki were to be accompanied by two additional planes besides the one carrying the bomb. The second plane was full of instruments, and the third was for photography. In the case of Nagasaki, the photography plane got lost, and there were no official photographs of that one, just one taken by the tail gunner on the bombing plane itself. As a reaction to what they had seen, some of the scientists at the lab attempted to petition the government not to drop the bombs on Japanese cities, but to drop them perhaps out in the ocean where Japanese government officials could see them, but no one would be harmed. This would have been a mistake. The truth is, a nuclear explosion at a safe distance is a beautiful and awe-inspiring sight. It's only when you see the victims that you realize the horror of the bombs that you've dropped. To understand the effects of fallout, we need to look again at the effects of radioactivity on living creatures. There are three kinds of radioactivity, besides fission: alpha, beta, and gamma. Alpha radiation is a little bit like fission. It's a reaction in which a large atom, large nucleus, permits a helium nucleus to escape from it. Helium nuclei are particularly stable compared with other low atomic number nuclei. And although they are held quite firmly in large nuclei, they do have a small probability of escape by a quantum mechanical process called tunneling. Beta radiation, the emission of electrons from the nucleus, we have shown to be involved in the transformation of an excess neutron in the nucleus into a proton with the emission of the negatively charged electron. But we haven't said much about gamma radiation. This picture shows how ordinary light is generated and absorbed by atoms. It doesn't happen in the nucleus, it happens between the nucleus and the electrons surrounding it, so that these electrons have specific energy levels they can occupy, and every electron is trying to reach its lowest energy level. It's trying to achieve stability, equilibrium. This is not a good thing for us living creatures, because our continued existence depends upon maintaining a state of instability, a state far from equilibrium, in which we expend energy in order to keep ourselves from achieving equilibrium, which we also call death. So we can see in this picture that a photon of light, electromagnetic radiation, is released as an electron falls from a higher to a lower energy level. If this photon strikes another atom, it can potentially excite one of its electrons to a higher energy level. Gamma rays are different from this. They are the same kind of photons of energy, but they come not from electron transitions in an atom, but from proton and neutron transitions within a nucleus. And just as the spacing of the energy levels in an atom is relatively close, so it only takes 2 or 3 electron volts to affect a transition between these levels, in the nucleus the spacing between energy levels is much greater. So when a nucleon decays to a lower energy state, it will emit a very energetic gamma ray photon. And it is the very energy of these photons which causes their effectiveness in hurting us, in creating a trail of ionized atoms within our tissues. Some of these ionized atoms may involve our DNA, and if so, it's possible that they can give rise to mutations which will eventually cause cancer in our cells. The scientists and engineers who worked on the Manhattan Project brought our species to the gates of hell. The politicians and military leaders who decided what to do with the products of the project stepped right through the gates.